is the best, of course. That's the only method that can solve any equation with order and operation. So it's the best case scenario, he will be the best. Second best, that's conjugate gradient. And number far down the list, you will find SOR. And even further down, Jacobi Gauss-Seidel. The material you have been given here is handwritten from Orset, a colleague of mine. Some years ago he was interested in this, and it's a fairly nice overview over multigrid. It's based mainly on this book by William Briggs, and you have this book in the reference list. Also you can find this book on the net, it's free. And it's a very cute, tiny little book, explaining it straightforward, practical, how this is done. Very easy to read. So most of the figures that you'll find in this material has been stolen then from Briggs. You also find a very short description in this compendium I wrote with the Navier-Stokes, how to include multigrid in this Sola algorithm. So that will be here in part 2. So there you have a very brief overview over what is multigrid and how you can test it. Also you can find, of course, many books now about multigrid, but be careful. You have some of these authors, Wesseling, Hackbusch. They are numerical people, and the books are extremely heavy. I don't think I ever seen any worse math with this numerical theory they are playing around with. It's awful, it's terrible. You can really scare even mathematicians. So the theory behind it, the numerical theory, can be very tough. But if you need a challenge, please seek them out. But now I will go through these multigrid part 1, 2 and part 3. Part 3, that's just an appendix. So we will begin here. And funny enough, and actually this is not unique for multigrid, it was found by the Russians. The Russians were very good, and still are, in numerical methods. And in the 50s, 60s, the reason was that they didn't have any money. They didn't have any computers. Well, they had, but they were very poor. Hence, they had to be very good numerical guys to make things work, to find a solution. The Americans, they just went out and bought a more powerful computer. So they didn't have to push themselves with the theory. The Russians were very good. And here Fedorenko came up with an article in the early 60s, but it took 10 years before anybody could understand what he was talking about. So it was Archie Brandt then that finally found the gold, you might say, how this can be done in practice. And then it exploded. So you have had a lot of articles since then, exponentially, using this method. So again, basic idea for multigrid, as I've said, you use these classical methods for solving an equation system, these simple Gauss-Seidel or Jacobi iterations. One iteration, also here called a sweep, over your entire domain, but only use very few iterations to get rid of high frequent noise. And then transfer your solution to a more coarsened mesh. There, this whatever noise you are left with on the fine mesh, where it appeared to be low frequent, now will appear more high frequent since you have fewer points to describe it with. And then do a couple of iterations there, a couple of sweeps. And then you take the solution back again to the fine grid, and then you should have a better solution. Here only 2 grid level is described. So of course you can have many grid levels, not only 2. We'll come back to that. Yeah, so here you have reference to Briggs and some of the more heavier ones, but be careful, they can be extremely tough, this numerical theory. So we start out here with the basics. Initially we start here with a matrix system, and the notation here is taken from Briggs, and now it's actually widely used, using matrix A, coefficient matrix, your unknowns U, and the right hand side F. Mathematician, he will typically write AX equals B, but complicated people, they use U and F. Here the wave indicates matrices and vectors. How had you achieved this one? Well, this is important, of course. For the example I showed you, that was the Laplace equation. From this one, you got the double derivative in all directions, so you ended up with something like this: I plus 1j, ti minus 1j, ti j plus 1, ti j minus 1, minus 4 times ti j should be 0. So that was the discrete version, using a constant mesh, delta x equals delta y. And then it's a question of solving this algebraic equation system. So here you will now write this one as a matrix system, and your coefficient matrix here, how will he look? Well, the diagonal, that's the center point, he will now look like this. He will have minus 4 all around, all the way down here. And then you have 4 neighbors. So at the line here you will have a 1, and the 1 you will have the closest neighbor in one direction, and then typically you will have some other 1s outside somewhere. So you will have a band here of 1s close to the diagonal, and then some other bands out here somewhere, maybe also coming in here somewhere, but most of the coefficients are going to be 0. So this means you never store the entire A matrix, the coefficient matrix. And I mean, why should you? It's 1 over minus 4, so what's the point? You don't have to store 1,000,000 of these numbers. So here you'll have all your unknowns, so t11, t12, all the way to tm, or whatever, equals, and for this equation here, equals to 0. So yes, you can solve this one directly, of course, if it's not too big. But remember, this A matrix consists then mostly of zeros in between here, but then you have some bands, depending on how many dimensions you have in your problem. But the point is here, this is not 0. This is 0, but this is of order delta x squared. It's a second order accurate, or depending on your scheme, some accuracy level here. Of course, it's possible now to take this algebraic equation system and solve it perfectly, down to machine accuracy. Yes, you can do that. But why should you? Because you have an adduct here anyway. So when you have an adduct who is a little bit smaller than this adduct, then you should be satisfied. it doesn't help to go any further. So to solve the equation system down to machine accuracy, that's sort of a waste of time and money. Possible, but why should you? So keep this one in mind. Where is the birth of your algebraic equation system? Well, it comes from a real equation, a real partial differential equation, discretized, then you get a matrix. This equation system will normally be linear. It doesn't have to be linear. Also depends on the original partial differential equation. You can have non-linearities, and then you will have trouble writing it as an equation system. But if it's linear, then we can play around with what's called a residual equation. First, this is also something that we need as a notation. We use a large omega to denote the different meshes. Omega superscript and then h. So that will be the finest mesh where we want the solution. So the smallest delta x. When we talk about coarser meshes, we will typically have twice the grid size. Then we will have an omega 2h, or 4h, or 8. So it will normally be a multiple of 2. So we use omega to denote the different meshes, and then also the unknowns will have a superscript h, denoting, okay, now it's the fine mesh solution. If it's U2H, and then it's a coarse mesh solution. U, that's the perfect solution to this one. And the one we are fighting with is the V. That's a numerical approximation to the exact solution. So we can hope that hope to find a V at least close to U. Defining the adode. There's the difference between U and V, and of course we want this adode to be as small as possible. To give a size for it, we use these two norms here. The infinitive norm, just finding the biggest one of all the adodes, absolute value. This to a norm, that's more used. Then you take the square root of the sum of the squares. So that's more of sort of an average value. Well, if you want an average value, you can put 1 over n in front here if you like. So the pure norm, he sort of includes all the adodes. The maximum or infinity norm, he just takes the biggest one. So when you have a numerical solution, an approximation to the correct one, you insert it, and now if you subtract f, or vice versa, you should get a number close to 0. Here we call it a residual. It's not going to be 0, but he's hopefully getting small. And of course we say we have a unique solution of this system, and that should normally be the case, no problem there. So the residual is 0, okay, that means the adode is 0. And now we can rewrite this equation system a little bit. Here you have the residual and your numerical approximation. So now you can they have added the original equation or subtracted it on each side. So here you now have the difference between the perfect solution and your numerical solution. And on the other side you will be left with the residual. So going from this step to this one, yes, you can do it if the matrix A is a linear coefficient matrix system. Then you can do this if your equation system is linear, and normally it will be. Then you can find this residual equation, as we call it. So the adode itself will also satisfy the same equation system. You sort of use the same philosophy behind the von Neumann stability analysis. You invent an adduct, look at it, and then you see that, okay, the adduct also satisfies my discrete equation system. And then you hunt down the adduct. You do the same here, this residual equation. But this is for a different reason, not stability, but efficiency. And the reason is as follows. When you have an equation system here on the fine mesh, you are seeking out your unknowns. Here the u's, that's what you want, but you have a whole bunch of v's. When you want to transfer the problem down to a coarser mesh, you cannot take in your solution and then taking sort of the same original equation down to a coarser mesh. Yes, you could. Instead, we will use the residual equation, because here it is not a problem to find the residual. I mean, you find it from the definition up here, r equals. That's just when your equation is not fulfilled. Yeah? So yes, you can find the residual fairly easy. And then you transfer this residual down to a coarser grid. And then you have to guess an adduct. And that's the nice thing. Of course you guess 0, because we want this adduct to be as small as possible anyway, so 0 is probably going to be a very good guess. And yes, it is. So that's the reason we use a residual equation, because we can invent good guesses for the adduct. If you would have used the original equation, then you would have had to do a lot of algebra to find your coarse mesh equation system. So normally we would like to do this, we want to do this, but the demand, your equation system must be a linear one, or else you can't do it. So normally it will be, so don't worry too much about it. So this is the residual equation. And also here, when you have, say, down on the coarse mesh, you have now solved your residual equation, you have found an adduct, then you go back to the fine mesh and adjust whatever solution you had here with the adduct you just found, and then you should get something at least closer to U. That will be the philosophy. So here, just a test case, a model problem, and that one you should be able to recognize. It's a one-dimensional equation. So you have the derivative of u with respect to y, I guess, equal to -1. Double derivative. Which then should be something like the Poisson equation, for instance, meaning you have the flow between two parallel plates, and then you insert a pressure to make it flow to the right, and you have a negative pressure gradient constant, and then you will get the solution, double derivative equal to -1, should be something like this. So you know the solution here. H then here being delta y. So now you can play around with the solution here in this equation system. And here you split it up into a coefficient matrix with 3 different parts, a diagonal and a lower part and an upper part. So the diagonal, that's one part, and then you have the lower triangle down here, that's the L, and then you have the upper triangle, that's this one. Now why do we do that? Well, we do it because now if we want to solve this one, iteratively, create an iterative process around this one. Then it's a question, is it Jacobi or Gauss-Seidel? Remember, Jacobi, then all these should be from the previous iteration. Then it should be n and n. Gauss-Seidel, then you're allowed to overwrite inside your code, inside each iteration. Then typically one of these will be from the same iteration level as him. So then it should be n plus 1 on either of these. And which one? Well, that will either be the lower or the upper triangle. So that's why we split it up here. So then you can define Jacobi iteration. Then you have both lower and upper. Should be from the previous. Everything should be from the previous iteration. Like this. And then you can use a weighted Jacobi method. Exactly the same theory here as when we designed this SOR. The modified Newton-Raphson method. Introducing here an omega. And to do it fast, you will then, of course, use an omega bigger than 1. But here you will then have a surprise, it will explode. Because remember, if you want an omega bigger than 1, you can't use Jacobi. Then it must be Gauss-Seidel. Then you can't use all the old values all the time. No way. So, but omega 1 bigger than 1, that's not the point here. We want actually omega equal to 1 or even smaller than 1. But then it had to be bigger than 1, it had to be Gauss-Seidel. Yeah, so here weighted Jacobi. So you can write it with this diagonal and lower upper. I don't really see the point actually. And again here with Gauss-Seidel, then depending on how you program it, of course, either the lower or the upper diagonal will be from the present iteration and not the previous. To make things easier, as a test case, you actually now do it like this. That's your test case. And then you say, I know the solution here. So for a fluid flow, that means you don't have any driving force in the system anymore. So your velocity is going to be 0. That's the solution. And we now create some initial field, which can be rather crazy. And then we see how fast can you get 0. Then you know if you have something different from 0, it's an adduct. So it's just a convenient test case, putting everything equal to 0. So then here you will have your 1D equation system. It will now look something like this, 0 on the other side. And now you can start playing around with initial noises, actually initial adducts, because everything different from 0 is going to be an adduct. So here we design some sine waves using a wave number k. And of course it's depending on how many points do you have. That will sort of limit the different the amount of different sine waves you can have. I mean, you need a certain amount of points to describe one sine wave. So here you have, I guess, 64 points or something. At least you can here see you can construct an initial field with different wave numbers. So k equals 1, just a half a sine wave, and 3 and 6, more and more high frequent. So that is the point. And this is now going to be the initial field for this equation here. And we are going to solve it numerically, then get rid of anything different from 0 as fast as possible. That is the aim. Yeah, the norm you don't have to look into. So here you will see the effect, as you have seen already, when you have very low frequent noise. K equals 1 here. And here you have then the number of iterations using Jacobi iteration. And the anode, you started with an anode of 1, and you see he hardly drops after 100 iterations. This is going to take forever. That was the same as you saw with this problem here. Initially, then he is moving very slowly. So with 3 half sine waves, well, the anode drops at least faster, and with 6, even faster. So the more high frequent, the better. The more efficient these iterative techniques will be. So the top one was then Jacobi, omega 2/3. The second one, that was the ordinary Gauss-Seidel iteration. And the last one here is called the red-black. You think in terms of a checkerboard pattern. You take first all the even points, and then afterwards all the odd points. It will still be a Gauss-Seidel, but the first half of your iteration will consist only of the previous values, since then every other point will be old ones. And then the second half, where you take all the odd points, then all of them will be updated. So it's still a Gauss-Seidel, and you see really not much difference between them either. One thing we can say, the Gauss-Seidel is more efficient than Jacobi, if you are thinking of finding the solution here. You get the number 6 here, and the number 6 here is fairly close to 0. So if you should find a solution, if that was the point, you should definitely use Gauss-Seidel. Have you used an omega here, bigger than 1, say close to 2, an optimum omega, this will be even sharper, absolutely. But still you will use many iterations to find a solution. And remember, this is a one-dimensional problem. If this had been a 3D problem, he wouldn't have read 100 here, he would have read 1 million or something. You need a lot of iterations to do this. Totally unpractical. This is not the point here. The point is finding an iterative method that can get rid of high frequent noise fast. That's what we are interested in. Yeah, the log just also shows that this is a linear one. And I think this one is a little bit more interesting. Yes. Here you can see more of the essence of being multi-grid. We have 64 points. And we use now the weighted Jacobi with omega 2/3, smaller than 1, there's under relaxation. And we design an initial field consisting of very low frequent, K is 1, and then medium frequent, K is 6, and then high frequent, K is 32. 32, that's more or less a sawtooth pattern. Remember, we have only 64 points. And now you can see the anode. You started initially with 1. All this is an anode. And then only after very few iterations, the anode has dropped substantially. So there you have the high frequent removal. Typically it will be this part. But then it levels off. And now this method becomes very inefficient. It's going to take forever to get the anode down to 0 or close to 0. But this part, this is interesting. Getting rid of the high frequent noise. Very interesting indeed. So this is what we are going to use. can set numbers on this. And now we are touching into numerical theory, which can be very heavy to follow. So don't pay too much attention to it. I'll never ask you about it. If you're interested, please have a look at it, but not so interested in this. Convergence rate, how fast does it go, and so on. You can do a lot here, but I think the math behind it, tedious, boring. We want a solution. But if you are interested in numerics, sure, a lot of things you can have a look at here. Writing it as a matrix system, look at the eigenvalues and so on. But rather boring. Yeah, so here is a question now with a limited number of points. How many waves can you design? So, of course, sooner or later you run into problems. Then you will have problems describing a proper sine wave. I mean, this will look more like noise, and if you're unfortunate with the spacing here, you can get something totally different actually. So you have to not overdo it, of course. So then, some terminology here. Smooth modes, oscillatory modes. So thinking in terms of low frequent noise and high frequent noise should be okay, I think. But they use also the word smooth and smoothers a lot in multigrid. Through this. You can read if you're interested. Different wave numbers. So typically here you have to choose one of these iterative techniques, how you want to get rid of the high frequent noise. And here the choice has fallen on Jacobi because it's more easy to analyze than the Gauss-Seidel scheme. But in practice, you don't see much difference in them. The only thing here is if you do a program, you will typically do a Gauss-Seidel without thinking. You have one vector with all your unknowns, and then you overwrite them continuously during your iteration process. That's Gauss-Seidel. If you want to use Jacobi, you have to create some temporary storage to avoid overwriting, because then everything should be based on the old values. So Gauss-Seidel is sort of easier to do. So here, test case with a weighted Jacobi, omega 2/3, and then you have constructed first. See how many iterations is there? It's 10 iterations. So here you start with your initial field, low frequency. So this is the adult. You know the solution is in 0. And then you do 10 iterations and you obtain this. Hardly anything has happened at all. Very inefficient on low frequency problems. Remember, this was Jacobi, omega 2/3. For a high frequent noise, then he has reduced it substantially after 10 iterations. A lot of this noise has been filtered out to almost nothing. So that looks very nice. And in the combination, you make a hybrid of these two modes. One very low frequent and then one very high frequent superimposed. After 10 iterations, you are left with this. So the high frequent are almost gone, and you are left with only the low frequent. But from now on, he's going to be extremely inefficient. Yeah, eigenvalues I won't go through. 2. So relaxation schemes, that is then one iteration using Jacobi, Gauss-Seidel or other. So we call that as relaxation, meaning one iteration, one relaxation. And as long as you have a high frequent anode, this is beautiful. They will be removed quite efficiently. If you have low frequent anode, you're in trouble. So that's what we know so far. And this property of the iterative scheme is then this smoothing property. We want him to be a very good smoother. That is something we are happy for. So yeah, the elements of multigrid here. He starts, I guess, with an never mind. So here, also a figure stolen from breaks. It's a little cheating actually, because here you have something, a signal, an anode on the fine mesh, omega super H. So this is the fine mesh. And you have a lot of points here, and then you are able to describe here a nice wave. But you see, there should be straight lines in between these points here. But never mind that. The same signal is now transferred or try to be drawn on a mesh omega 2H. This is a mesh then with just each cell here is twice as big as the one up here. So you only have every second point. So it's hardly the same image. But as I said, they have cheated a little bit. They used some curved lines up here. Never mind. So the point is, this wave on the coarse grid here definitely is very high frequent. It appears very high frequent. While up here, it's not that much change between the points, so yes, definitely more low frequent. So it's the frequency here, remember, nothing to do with the spacing. So using coarser and coarser grid, that will be, it's not the gradients we are looking at, it's just the change in neighboring points. So how far it is between the 2 points, that doesn't matter. So it's just the frequency here that is interesting, not the distance between the points. Yeah, this is not so important here. So again, back to the residual equation. You start iterate on the fine mesh. This is the equation you try to solve. You update your unknowns, and then you check, is the residual close to 0 now? If it is, then you have the solution. If it's not, then you take this residual and you move it to a quotient grid, and then you try to solve this equation for the anode on the coarse mesh. And when you find the anode, you update your velocity or your unknown, hopefully finding a better one. So the residual equation, as it says here, is a very convenient choice, since you can guess initially that the anode should be 0. Very good initial guess. So that's a very good idea. And the requirement equation system had to be linear before you can do that. So here a more detailed algorithm. You start here, actually here they start on a coarse width, because you haven't even gotten an initial field. So you start where it is very cheap. Start on a very coarse mesh and see if you can find a solution there. When it says relax, that means one iteration or maybe several. So relax on this equation system on a very coarse mesh, and then you push your solution on a finer and finer mesh. Here we are on omega 4H, and use this one to find a good guess for omega 2H, and so until you have a good initial guess on the finest mesh. So now we can start again on the fine mesh. And this is your equation we are trying to solve. And now on the fine mesh, omega h, we are seeking our numerical solution there. And we do a couple of iterations. And then we calculate the residual. And then we take this residual and push him onto a coarser mesh, omega 2H, with initial anode 0, and then try to solve this one, or at least we iterate a couple of times on it, and then we can go back again to correct the unknown that we had up here, using this anode. Actually, this anode superscript 2H. So this will be the adjustment equation then. Your first solution that we had up here, and then we have found an anode on the coarse mesh. Now we adjust him to finding a better solution on the fine mesh. So here, this is just a two mesh system. So either two mesh or just a coarse grid correction scheme. So to do this, we are going to need to know how to, well, finding the residual, that shouldn't be too hard. And how to move the residual from one mesh to another. That's something we need to know. And here, finding the anode, or iterate here on the anode on the coarse mesh, that should be easy. But how to transfer it back to the fine mesh? That is also something that we need to look into. So that's what we call intergrid transfers, which will be the next thing we have to look at. Questions so far? Then we take a break.